Hello everyone, welcome back. In the last video, we looked at the different methods that we can use to solve certain types of limits. And now that we have an underlying idea behind limits and ways of calculating them, we can now use them to define what it means for a function to be continuous at a point and continuous on an interval. We can then explore the intermediate value theorem and its application of locating the roots. Now, the way that we define a continuous function in this course is going to be very similar to the everyday use of the word continuous. If you think about a process that is continuous, you might think of something that has no gaps or has no breaks. So a way that you can think about what continuous functions look like, well, if we can draw the graph of the function without having to lift up our pen, then this is a continuous function. So there are no gaps or breaks in the graph. On the other hand, if we have to lift up our pen, then this may not be a continuous function at a particular point. So what conditions do we need in order for us to say that a function is continuous at a given point? Well, let's have a look at some of our earlier examples to see what the conditions are. So for these functions, we're looking at what happens when x is equal to 2. So for each of these graphs, what we notice is that there are different behaviors when x is equal to 2. If we look at the left graph, what we see is that the function is defined at the number 2 and its value is equal to 4. And this graph is an example of a function that is continuous at the point where x is 2. Recall that we determined that the two-sided limit of f of x as x approaches 2 is also equal to 4. Now, if we look at the second graph, what we notice is that the function is not defined when x is 2. And this function is not continuous at this point because there is a gap at x equals 2. In the third example, the function is defined when x equals 2. However, the value of the function is not equal to 4. What we see is that the function value where x equals 2 is equal to 3. So the function value is different from the two-sided limit as x approaches 2. So after examining each of these different examples, we can now look at defining what it means for a function to be continuous at a given point. So what we say is that a function f is continuous at a number a if the limit of f of x as x approaches a is equal to f of a. So if we look at the first example, we saw that the function value where x is 2 is equal to 4. We also see that the two-sided limit as x approaches 2 is also equal to 4. So the two-sided limit as x approaches 2 is equal to the function value where x equals 2. And so since the limit as x approaches 2 of f of x is equal to f of 2, then the function is continuous at the point where x is equal to 2. So the definition of continuity actually implies 3 different conditions. So in order for a function to be continuous at a given point, the following conditions must be satisfied. So the two-sided limit as x approaches a must exist, the function needs to be defined at the point a, and the two-sided limit as x approaches a must equal the function value where x equals a. Now, if any of these conditions are not satisfied, then what we say is that the function is discontinuous at a. So for example, if we look at the second graph from before, what we see is that the two-sided limit exists, but the function is not defined at the point where x equals 2. So the second condition is not satisfied for the second graph. Now if we look at the third example, we see that the function is defined at the point where x equals a. The two-sided limit exists. However, the two-sided limit does not equal the function value at a. And so the third condition is not satisfied for the third example. So now let's have a look at classifying the different types of discontinuities that we can encounter. So the discontinuity that we see in 2.12 or 2.13 are examples of removable discontinuities. And they're called removable discontinuities because we can simply remove the discontinuity by redefining the function. So we know that the function was not continuous at x equals 2. So if we were to redefine this function so that the function obtains a value of 4 where x equals 2, then we can make the function a continuous one. And similarly, if we were to change the value of f when x equals 2 to be equal to 4 rather than 3, then again we can remove that discontinuity by redefining the function. Now another kind of discontinuity that can occur is when the limit of f of x as x approaches a goes to plus or minus infinity. And these are called infinite discontinuities. A jump discontinuity occurs if the left and the right-sided limits do not equal the same value. So here are some examples of an infinite and a jump discontinuity. So here we see that the function as x approaches 1 goes to infinity from both sides. So we have an infinite discontinuity when x equals 1. On the right graph, what we have is a function where as x approaches 1 from the left, it goes to a value of 1. And if we approach 1 from the right, then the value is going to negative 1. And so the left-hand limit goes to 1, the right-hand limit goes to negative 1. So there is a jump discontinuity at x equals 1. We say that a function is continuous on an interval if it is continuous at every number in that interval. So now let's have a look at some examples of determining whether functions are continuous at a given point. So in the first example, we have a piecewise defined function. So the function f is equal to 1 over x plus 2 if x is not equal to negative 2, and the function is equal to 1 if x is equal to negative 2. So we want to know if the function is continuous at the number negative 2. So one of the conditions for continuity was that the two-sided limit as x approaches a, so in this case negative 2, must exist. So we'll first check whether or not this limit exists. So we want to calculate the two-sided limit as x approaches negative 2. So what is f of x equal to if we let x approach negative 2? Now recall that we are taking the limit as x approaches negative 2, so we're not letting x be equal to negative 2, but very, very close to negative 2. And if x is not equal to negative 2, then the function will be equal to 1 over x plus 2. And so what we have is the limit of 1 over x plus 2 as x approaches negative 2. So now we will take the limit. So if we let x go to negative 2, we get 1 over negative 2 plus 2, which is 1 over 0. And 1 over 0 will go to a very large number. However, depending on whether if we approach from the left of negative 2 or from the right of negative 2, then this limit may end up going to a different value. So what we need to check are the left and the right-sided limits. So let's have a look at taking the limit as x approaches negative 2 from the left. So if we let x go to negative 2 from the left, we end up with 1 over 0. Now, since we're approaching from the left of negative 2, we can think of x as being a value that is slightly smaller than negative 2. So for example, negative 2.0001. And if we add 2 to x, then we're going to get a very small number, close to 0, but it will be negative. And so what we have is 1 over 0 minus, so a very small negative number. And 1 over a small negative number goes to negative infinity. So now let's also check the right-hand limit. So let's approach negative 2 from the right. And so if we let x go to negative 2 from the right, we get 1 over 0. And now we need to determine whether this is a small positive or a small negative number. So if we're approaching negative 2 from the right, then x will be slightly larger than negative 2. So for example, negative 1.9 repeating. And if we add 2 to this value, we will get a very small positive number. Okay, so this will be 0 plus. So we have 1 over a very small positive number, and this will go to positive infinity. So if the left-hand limit goes to negative infinity and the right-hand limit goes to positive infinity, then what we can say is that the left-hand limit does not equal the right-hand limit. So then the two-sided limit as x approaches negative 2 of 1 over x plus 2 does not exist. And since the two-sided limit does not exist, the function is not continuous at the point where x equals 2. So now let's have a look at the next example. So we have our function, which is defined as 1 minus x squared if x is less than or equal to 1, and it's the natural logarithm of x if x is greater than 1. And we want to know if this function is continuous at the point where x is 1. So let's have a look at the two-sided limit as x approaches 1. So now, because the function is defined differently if x is less than 1 or if x is greater than 1, we're going to need to look at the one-sided limits separately. So let's have a look at the left-hand limit. So let's approach 1 from the left. So if we're approaching 1 from the left, then you can think of x as being a value that is slightly smaller than 1. And f of x is equal to 1 minus x squared if x is less than or equal to 1. So what we have is that the limit as x approaches 1 from the left is 1 minus x squared. So now we can take the limit. So if we let x go to 1, we end up with 1 minus 1 squared. So that's 1 minus 1, which is 0. Now for the right-hand limit, we're going to approach 1 from the right. And if x is approaching 1 from the right, then x will be slightly larger than 1. And if x is larger than 1, then f of x will be equal to the natural log of x. So what we have is that the limit of f of x as x approaches 1 from the right is equal to the limit of the natural logarithm of x. So then we can take the limit. So we will substitute the value of 1 for x. So we end up with the natural log of 1. And what is the natural log of 1? Well, this is equal to 0. So it's the exponent on the base of e, so that it is equal to 1. And if x is equal to 0, then e to the 0 will be equal to 1. And so the natural logarithm of 1 is 0. So since the left-hand limit is equal to the right-hand limit, then we can conclude that the two-sided limit as x approaches 1 of f of x is equal to 0. And so the two-sided limit So now we need to check if the function is defined at 1. So what is f of 1? So if x is less than or equal to 1, then the function will be equal to 1 minus x squared. So to find the function value at 1, we're going to substitute 1 into the first function. So we have 1 minus 1 squared. So that is 1 minus 1, and that is equal to 0. So we have that f of 1 is equal to 0. So it is defined at 1. And now the last thing to check is if the two-sided limit is the same as the function value at 1. So we see that the two-sided limit is equal to 0, and the function value is also equal to 0. So since the limit as x approaches 1 of f of x is equal to f of 1, then we can conclude that the function is continuous at 1. So now in the third example, we have our function, which is defined as the cosine of x if x is less than pi over 4, and it is equal to the sine of x if x is greater than or equal to pi over 4. And we want to know if this function is defined at pi over 4. And so the first thing we'll check is the two-sided limit. So let's approach pi over 4 from both sides. And again, because the function is defined differently if we approach pi over 4 from the left or from the right, we're going to need to look at the one-sided limit. So let's have a look at the left-hand limit. So let's approach pi over 4 from the left. So if we're approaching pi over 4 from the left, then x will be slightly smaller than pi over 4. And if x is smaller than pi over 4, then the function will be equal to the cosine of x. And so for the left-hand limit, our function is the cosine of x. And now we can take the limit. So if we let x go to pi over 4, we get the cos of pi over 4. And now what is the cosine of pi over 4? So here we can use either the unit circle or special triangles. So we want the pi over 4 triangle. And that is 1, 1, and root 2 for the sides of this special triangle. And the cosine is the adjacent side over the hypotenuse. And so cosine of pi over 4 is 1 over the square root of 2. And if you want, we can rationalize this to root 2 over 2. So now let's also look at the right-hand limit. So let's approach x from the right of pi over 4. And if we're approaching pi over 4 from the right, then x will be slightly larger than pi over 4. And so our function will be equal to the sine of x if x is greater than or equal to pi over 4. So what we have is the limit as x approaches pi over 4 from the right of the sine of x. So now we can take the limit. So if we let x go to pi over 4, we end up with the sine of pi over 4. And the sine of pi over 4 is going to be the opposite side over the hypotenuse. So if we use the same special triangle, we get 1 over the square root of 2. And if you rationalize this, this will be root 2 over 2. So now since the left-hand limit is equal to the right-hand limit, then the two-sided limit as x approaches pi over 4 will be equal to the square root of 2 over 2. So next we need to check that the function is defined at pi over 4. So if x is equal to pi over 4, then the function f of x will be equal to the sine of x. So to evaluate f at pi over 4, we're going to use the bottom function. So we're going to substitute pi over 4 for x. So we end up with the sine of pi over 4, which we know to be 1 over root 2 or root 2 over 2. So the function is defined at pi over 4. And now the last step is to check that the two-sided limit as x approaches pi over 4 is equal to the function value at pi over 4. So we see that the two-sided limit is root 2 over 2, And the function at pi over 4 is also equal to root 2 over 2. So since the two-sided limit of f of x as x approaches pi over 4 is equal to f at pi over 4, then we can conclude that the function is continuous at pi over 4. So in the second example, we are looking for the numbers at which the function f is discontinuous. So our function is defined as a piecewise defined function. So it's equal to x squared if x is less than -1. It's x if x is greater than or equal to -1, but less than 1. And it's 1 over x if x is greater than or equal to 1. So what we'll note is that each piecewise defined function is defined or rather it is continuous in each of their respective domains. Now the points where the function may not be continuous is when the domain changes. So possible points of discontinuity are where the function changes domain. And these happen when x is -1 and when x is +1. So the 2 points where the function may not be continuous are at these 2 points. And so what we need to check is the definition of continuity at -1 and at +1. So let's first have a look at -1. So we'll check the two-sided limit. And since the function will depend on whether we approach -1 from the left or from the right, then we're going to need to look at the one-sided limits separately. So we'll check the one-sided limits to -1. So if we approach -1 from the left, so x is smaller than -1, then our function f of x will be equal to x squared. So the left-hand limit to -1 is of x squared, and then we can substitute our limit into our function. So we have -1 squared, which is +1. Now if we approach from the right of -1, so now x will be slightly larger than -1, then our function f of x is going to be equal to x. Okay, so if x is greater than or equal to -1, but smaller than 1, then our function f will be equal to x. And so our function is equal to x. And now if we take the limit, we get -1 for the right-hand limit. So now since the left-hand limit goes to 1 and the right-hand limit goes to -1, then the two-sided limit does not exist. So since the left-hand limit does not equal the right-hand limit, then the two-sided limit going to -1 of f of x does not exist. And since the two-sided limit does not exist, we know that f of x is not continuous at -1. So now let's check the conditions for continuity at +1. So first, let's look at the two-sided limit going to +1. And again, because our function f of x is defined differently if we approach +1 from the left or from the right, we will need to look at the one-sided limits separately. So let's have a look at the left-hand limit to +1. So if x is slightly smaller than 1, then f of x will be equal to x. And so we have the limit as x approaches 1 from the left of x. And then if we take the limit, we get 1 for the left-hand limit. So now let's have a look at the right-hand limit. So now x will be slightly larger than +1. And if x is larger than +1, then our function will be equal to 1 over x. So we have the limit as x approaches 1 from the right of 1 over x. And if we take the limit, we get 1 over 1, which is equal to 1. And since the left-hand limit is equal to the right-hand limit, then the two-sided limit as x approaches 1 of f of x is equal to 1. And so this tells us that the two-sided limit exists. So now let's check if the function is defined at +1. So if x is equal to 1, then our function f of x is equal to 1 over x. So to find f of 1, we're going to evaluate the function at 1 over x. So we have 1 over 1, which is equal to 1. So what we see is that the function is defined at 1. And the last thing to check is if the two-sided limit is equal to the function value at 1. So what we see is that the limit as x approaches 1 of f of x is equal to f of 1. So we can conclude that the function is continuous at x equals 1. For the third example, we are looking for the value of the constant c that will make f continuous on the real numbers. So here our function is defined as cx squared plus 2x if x is less than 2, and it's x cubed minus cx if x is greater than or equal to 2. So this function is defined except possibly when the domain changes. We see that the domain changes when x is equal to 2. So what we want to do is look at the definition of continuity when x equals 2. Alright, so the first thing we'll check is the two-sided limit. So let's approach 2 from both sides. And since the function will depend if we're approaching from the left or the right of 2, we're going to have to look at the one-sided limit separately, as before. So let's have a look at the left-hand limit. So if we're approaching 2 from the left, x will be slightly smaller than 2. And if x is smaller than 2, our function is cx squared plus 2x. So we have the limit as x approaches 2 of cx squared plus 2x. So now if we take the limit, we're going to let x go to 2. We have c times 2 squared plus 2 times 2, and this will give us 4c plus 4. So that's our left-hand limit. Let's have a look at the right-hand limit. We have the limit as x approaches 2 from the right. And if we're approaching 2 from the right, x will be slightly larger than 2, and our function will be equal to x cubed minus cx. So now taking the limit, we're going to let x go to 2. We have 2 cubed minus c times 2. So this is 8 minus 2c. Now, since we want the function to be continuous for all real numbers, we know that the two-sided limit must exist. And in order for the two-sided limit to exist, we need the left-hand limit to be equal to the right-hand limit. And so what this says is that the left-hand limit, which we determined to be 4c plus 4, it has to be equal to the right-hand limit, which we determined to be 8 minus 2c. So for it to be continuous, this equation must be satisfied. So now that we have an equation that involves c, we can now solve for c to determine what the constant that we need in order for the function to be continuous. So we have 4c plus 2c is equal to 8 minus 4. So 6c is equal to 4. So solving for c, we get 4 over 6, or 2 over 3. So the constant c that will make the function continuous is 2 over 3. So the next two theorems will talk about which types of functions are continuous. So any polynomial is continuous, and it's continuous on the entire domain. So it's continuous on all real numbers, and any rational function is continuous wherever it is defined. So it is continuous on its domain. Then the following types of functions are also continuous in their domains. So this will include the two that we've mentioned already. It will also include the root functions, the trig functions, the exponential functions, and the logarithmic functions. Now the next theorem is called the intermediate value theorem. And what it says is that suppose we have a continuous function on a closed interval from a to b, and let n be any number between f of a and f of b, where f of a is not equal to f of b. Then there exists a number c within the interval from a to b such that f of c is equal to n. So what does this theorem state? Well, suppose we have a continuous function, and it's continuous from the interval from a to b. So there are no gaps within this function on this interval. And suppose that the function value at a is given as f of a, and the value at b is given at f of b. So for every value in between f of a and f of b, then there has to be some value c that's between a and b, such that the function f will take on the value of n. So the function has to attain every value between f of a and f of b, and moreover, it has to attain the value within the interval from a to b. Now let's suppose that we have a function and we know that at a, let's suppose that the function is positive. And then at b, suppose we know that the function is negative. And if f is continuous from a to b, then the function has to attain a certain value. It has to pass through the x-intercept, meaning that the function has to be 0 for some value c within a and b. So the intermediate value theorem is useful for locating the roots of a function. So let's have a look at an example of using the intermediate value theorem to show that there is the existence of a root within a certain interval. So here we have the equation x to the power of 4 minus x minus 3. This equals 0. And we want to show that there is a root of this equation within the interval from 1 to 2. So here we want to use the intermediate value theorem. So we need to define our function, f of x. So we're going to let our function be equal to the left-hand side of the equation. So we'll let it be equal to x to the 4 minus x minus 3. Then solving the above equation is equivalent to showing that there is a root of the function on the interval from 1 to 2. So now we need to look at the signs of the function values at the endpoints of our interval. So we're going to evaluate the function at the endpoints, so f of 1 and at f of 2. So we have 1 to the power of 4 minus 1 minus 3. So this is 1 minus 1 minus 3, which gives us negative 3. So we're given that f of 1 is negative, so it's less than 0. Now let's have a look at f of 2. So we're given that f of 2 is 2 to the power of 4 minus 2 minus 3. So that is 16 minus 5, which is 11. So this tells us that f of 2 is positive. Our function is a polynomial, which is continuous on all real numbers. And so the conditions for using the intermediate value theorem are satisfied. So by the intermediate value theorem, which I will shorthand to IVT, since f of 1 is negative and f of 2 is positive, then we know that the function has to be equal to 0 for some value c within the interval from 1 to 2. So since the function is negative at 1 and then it's positive at 2, it has to pass through the x-axis, meaning that the function has to be 0 for some value between 1 and 2. So that tells us that the equation x to the power of 4 minus x minus 3 equals 0 has a root on the interval from 1 to 2. So here is the graph of the function x to the 4 minus x minus 3. So what we found was that the function value at 1 is negative 3, and the function value at 2 is positive 11. And because the function is continuous, it has to pass through 0 at some point between 1 and 2. And so we show that there is a solution on the interval from 1 to 2.